Okay, let's go ahead and do our last piece of trig substitution. Got a couple of more examples, and then we'll move on to the next section. Um, let's go ahead and start with this one, 16 minus 4x squared. That's a little bit different because we don't have 16 minus x squared. We don't have 4 minus x squared. It's 16 minus 4x squared. Now, you could go ahead and factor the 4 out, resolve the square root of 4 and call it a 2 and pop a 2 out in front. Or you could just keep it all together. It really doesn't matter. It's just a matter of when you factor out. I would just leave it. I would just say, well, 4x squared is going to need to be 16 sine squared theta. So that just means x squared is equal to 4 sine squared theta, or x is equal to 2 sine theta. See, it's just one extra step here. Sine theta is equal to x over 2. We'll need that a little bit later. Dx is equal to 2 cosine theta d theta. Alright, so that's really all the information that I need in order to go ahead and do my substitution. I have 16 minus 16 sine squared theta. Now my dx is 2 cosine theta d theta. Now this right here, of course, winds up being 16 cosine squared theta underneath, so this winds up being 4 cosine theta. And if that's the case, then this winds up being 8 cosine squared theta d theta, or 4 1 plus cosine 2 theta d theta. Okay? So this winds up being 4 d theta plus 2 cosine 2 theta, because I'm going to steal one of those 2's and put it with the d theta to set myself up for u sub. 4 theta plus 4 sine 2 theta plus c. And, we can go ahead and do the 2 sine theta cosine theta by using our double angle identity for sine. Now, let's go ahead and set up the triangle. We have opposite over hypotenuse, and this winds up being 4 minus x squared. Now, does this look familiar? It should. It's a multiple of this, or in fact, this is a multiple of that, okay? Because, like I said, you could have, by factoring that out, transformed this into that. That would have been the equivalent, integral. From here, I know that theta is arcsine x over 2. I know that sine of theta is going to be x over 2. And I know that cosine of theta is going to be the square root of 4 minus x squared over 2 plus c. Okay? Well, in that case, I recognize the fact that this 2 and that 2 are going to cancel out. And I get 4 arcsine x over 2 plus 1/2 x 4 minus x squared plus c, and that should be easy enough. Now the next one, this is one of those ones where when you get to the test, you really want to remember the old saying, stop, think, then do. Because this one is only different from the previous one because there's an x right here. But that's the difference between one that I can use trig sub on and one that I must use trig sub on. This one is u sub. All I have to do, and this one I am going to go ahead and pull out the 2, and that makes x, and then 4 minus x squared dx. Let's let my u equal to 4 minus x squared, and therefore my du is negative 2x dx. I'm going to go ahead and borrow that 2. We'll leave a negative out in front. U to the 1/2 du. And then from here, I'm going to get negative 2/3 integral, or u to the 3/2 plus c, or negative 2/3 4 minus x squared to the 3/2 plus c. Right? Now, can I do this one by trig sub? Sure, I would just use the same sort of substitutions that I had in the last one. You know, x is equal to 2 sine theta. I would just have an extra 2 sine theta here. 16 minus 16 sine squared theta times 2 cosine theta d theta, and that would be the trig integral that I would have to deal with. And it actually wouldn't really be all that difficult because there would be that extra sign in there. I wouldn't have to do power reducing. I could just do u sub. But obviously, if I'm gonna, just u sub from the very beginning gets me out of that bind, and I don't have to worry about doing any trig sub whatsoever. So that's always nice. Let's go ahead and do a couple more examples. For a difficult section like this, I think about 3 videos is usually about all you're going to get through, but I think it's enough and not too much. So now this one, you have to use trig sub, right? It's a difference, so it's not tangent, and the constant comes last, so it's going to be secant. I need x squared equal to 4 secant squared theta because x is equal to 2 secant theta. I know that dx is equal to 2 secant theta tangent theta d theta, and that gives me everything that I need at present in order to go ahead and substitute in. Let's go ahead and do that numerator, that dx in the numerator first, and then we'll sub in down here, and we're going to get 4 secant squared theta minus 4. Well, the 4 secant squared theta minus 4 wind up being 2 tangent theta the moment that you actually, do the whole trigonometric identity. So that cancels out with this and this. Boom, boom. And what I'm left with is actually just a very simple secant theta d theta. Well, if you remember, that's natural log of secant theta plus tangent theta plus c. And now all I have to do is set up my triangle and get expressions for secant theta and tangent theta. Well, I obviously already have one for secant theta, right? Secant theta, and of course secant is going to be hypotenuse over adjacent. This winds up being x squared minus 4. Hope nobody's surprised. And this winds up being x over 2 plus the square root of x squared minus 4 over 2 plus c. And that is my integral. All right. Well, this is going to be probably a little bit shorter video than usual. I only really have one more example that I want to go over with you. Okay. How about dx over x, 4x squared plus 16? Now remember, because it's got the 4x squared, I always start out with what do I want that expression to be? And that expression I want to be 16 tangent squared theta. So x squared is obviously 4 tangent squared theta, and x is equal to 2 tangent theta. Well, we'll need this relationship later. Tangent theta is x over 2. We'll need this relationship right now, though, the differential. So we'll need 2 secant squared theta d theta in the numerator. We'll need 2 tangent theta, and then of course what the radical is, which is 16 tangent squared theta plus 16. Well, 16 tangent winds up being 16 secant squared underneath the radical, or 4 secant. So 4 secant theta. Well, let's just do a little bit of cancellation right now. I know that one of those secants will cancel out with that secant. I know that those 2's right there go bye-bye. And I'm left with secant theta d theta over 4 tangent theta, or 1/4. And this winds up being, if it's secant theta over tangent theta, you know that that's 1 over cosine times cotangent. All right, that's the same thing. When in doubt on how to reduce it, just go ahead and turn it back into sine and cosine. And that winds up being 1/4 secant theta. Well, that's a very similar integral by identity. I've already shown you that one before. And you get natural log of cosecant theta minus cotangent theta plus c. So the only thing that's left to do, draw my triangle, get my cosecant and my cotangent. Now I know that tangent is equal to x over 2, so this is going to wind up being x squared plus 4. This, of course, is a multiple of that, of the square root of x squared plus 4. And I recognize the fact that cosecant is going to be hypotenuse over opposite, x squared plus 4 over x, and cotangent is just going to be the reciprocal of tangent, which is 2 over x. And there you go. And that winds up being, and that's just example after example after example of ones that have a binomial radicand, whereby you can plug in, change the form, such that you can actually change the integrand into something that can actually be done, do it, and then substitute back using your triangle and your knowledge of trig and inverse trig and all sorts of fun stuff like that. Okay, that is it for our couple of videos on trig sub. Next, there will be videos on the trapezoidal rule, which is actually rather straightforward. There's just a couple of quirky ways that people on the AP, people who write the AP exam, like to ask questions about it. So we may have 2, we may have 3 videos on that, depending on how many of those quirky little ways we actually want to explore. And then from there we'll get on into improper integrals, which are, of course, a whole lot of fun. Any questions? Email me. Bye.